Every time your app touches a database, it pays a latency tax. A single query might cost 10 milliseconds. That sounds small, but at 100,000 requests per day, it adds up fast. The solution engineers have been reaching for since the 1970s is a cache. And not just any cache. The one design that keeps showing up everywhere, from your phone's CPU to Redis, from your browser to DNS resolvers, is called an LRU cache. Today we are going to understand exactly why. Here is the problem in raw numbers. Without a cache, every single user request hits your database. 100,000 requests means 100,000 disk reads, each costing 1 to 10 milliseconds. With an LRU cache in front of that database, 99% of those requests get answered from memory in a tenth of a millisecond. The database only sees 1% of the traffic. That is 100 times speedup for the cost of a few hundred megabytes of RAM. The asymmetry is almost absurd once you see it. So what exactly is an LRU cache? LRU stands for least recently used. You give the cache a fixed size, say 1,000 items. When it fills up and you need to store something new, you evict the item that has not been touched for the longest time. The intuition is simple. If you have not needed something recently, you probably do not need it right now either. The slots you see here represent the cache contents, ordered from least recently used on the left to most recently used on the right. New accesses promote an item to the far right. Stale items drift leftward until they are evicted. Get both lookup and eviction down to O of 1 time complexity. You need two data structures working together. A hash map gives you constant time lookup by key, returning a pointer directly to a node. A doubly linked list maintains the recency order of those same nodes. Because you have a direct pointer from the hash map to the list node, you can move any node to the tail in O of 1, no traversal required. The head of the list is always the least recently used item, ready to be evicted instantly. Neither structure alone achieves this. Together, they make every single operation constant time. GET operation has two outcomes. On a cache hit, you look up the key in the hash map, move that node to the tail of the linked list to mark it as most recently used, then return the value. 3 steps, all O of 1 node database involved. On a cache miss, you fetch the value from the database, create a new node, insert it at the tail, and if the cache is full, you remove the head node and delete its entry from the hash map. Both paths complete in constant time. The only variable cost on a miss is the database round trip itself. The PUT operation is what you call after a cache miss when you have fetched fresh data. The before state shows the cache at full capacity. When you put a new key, the head node, which is the least recently used item, is unlinked from the list and its key is removed from the hash map. The new node is appended at the tail and added to the hash map. Notice how the before and after rows show exactly which item disappears and where the new entry lands. 4 pointer updates and 2 hash map operations, all O of 1 regardless of cache size. The reason LRU works so well in practice comes down to a property of real workloads called temporal locality. Data that was accessed recently tends to be accessed again soon. Your home page gets hit 10,000 times a day. A page from 5 years ago gets hit once. Your active user rows are queried constantly. Deleted accounts are queried never. LRU exploits this skew automatically, keeping hot data resident and letting cold data fall off the list naturally. That is why it outperforms simpler policies like FIFO, which ignores recency, or random eviction, which ignores everything. LRU is not just a theoretical construct. Redis uses all keys LRU as its default eviction policy when RAM fills up. Your CPU's L1 and L2 caches use LRU-like policies in hardware to decide which memory lines to keep, shaving nanoseconds off every instruction. Chrome's HTTP cache uses LRU to manage which JavaScript, CSS, and images survive between sessions. Your operating system's DNS resolver caches domain lookups using LRU, so popular domains like Google.com never need a fresh lookup. Every layer of the modern software stack uses this same idea. LRU is not perfect for every workload. Sequential scans are its biggest enemy. If your code does a full table scan over 10 million rows, every row floods into the cache in order and evicts all your hot data. After the scan, your hit rate collapses from 95% to near zero. This is called cache thrashing. For workloads with scan patterns, engineers reach for LRU-K, which requires a key to be accessed K times before it enters the hot zone, making it scan resistant. Adaptive replacement cache used in ZFS maintains two lists and self-tunes the boundary. W-TinyLFU, the algorithm behind the Java caffeine library, combines a frequency sketch with a small LRU window and delivers the best measured hit rates in production benchmarks. LRU caches are everywhere because they solve a fundamental mismatch. Compute is fast, storage is slow, and workloads are skewed. A small amount of memory holding the right 100 items can absorb the load that would otherwise crush a database. The data structure is elegant, the implementation is straightforward, and the performance gains are immediate. Whether you are building a web service, tuning a database, or designing a CPU, the LRU cache is one of those ideas that pays for itself every single time. Thanks for watching.